Hello guys, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in the last session of gravitation chapter, we discussed about the gravitational field and the acceleration due to gravity, right? So how the acceleration due to gravity changes if we go above from the earth surface and some depth below the earth surface, right? So in both the cases it decreases, and we have seen the mathematical calculations, and we have solved some questions also related to that, right? So today we are going to deal with the lecture number 3 of gravitation, where we are going to focus on how the acceleration due to gravity changes due to the shape of the earth, and how the acceleration due to gravity changes due to the rotation of the earth. And then we are going to deal with one more important concept, that is gravitational potential, and at the end of the lecture we'll see the relation between the gravitational field and the gravitational potential. So these are our 4 objectives of today's session. Okay, I just need your attention for the next 1 hour, guys. Just be with me, avoid all the disturbances around you, and at the end of the lecture it's very important to prepare your own short notes, and when you are coming to the next lecture, revise the previous short notes. Okay, so if you have any backlogs, clear them now. So don't create any backlogs, guys, because you are in the class 11th now. So if you create backlogs, so it will be a burden for you again, so you'll not understand further chapters also. Okay, you have time now, so just clear your backlogs and be with the flow. Okay, chalo, so let's get into the topic without wasting much time. So first, how the acceleration due to gravity changes due to the shape of the earth. See, generally the earth is of some elliptical shape. Okay, so not this much, but somewhat like this. So like this maybe. So somewhat elliptical, not completely solid sphere. So it looks somewhat like this. So if we observe the shape of this earth now, so there will be 2 radii for the earth. So one is the equator, this one, and then this is the pole. This is the equator ends, these are the pole ends, right? So the radius of the equator is greater than the radius at the poles. The radius at the equator is greater than the radius at the pole. Okay, so we know that the g, small g value is equals to gm by r square. So from here you can say that the acceleration due to gravity is inversely proportional to square of the radius, right? So now as re is greater than rp, so shall I say that so the acceleration due to gravity at equator will be less than the acceleration due to gravity at the poles. Okay, so this is the actual concept, guys. So earth, we assume it as a solid sphere, but in reality it's not exactly the solid sphere. It looks like somewhat elliptical shape, not completely like this, but some torted. It will be torted at these ends. Okay, so somewhat elliptical. So if we observe, so the radius at the equator will be greater than the radius at the pole. So we know that g is inversely proportional to r square. So the acceleration due to gravity at the equator so will be less than the acceleration due to gravity at the pole. So this difference is not going to be very big. It's going to be very small. So the variation in g at the equator to the pole, so it's going to be very small, approximately 0.5% only. Okay, so I'll give the values also. So the acceleration due to gravity at the equator, it is 9.78, approximately it is 9.78 meter per second square. And then so the at the poles it will be so 9.8 meter per second square. So very small change. Okay, clear, guys? So as we go from equator to the pole, so the g value increases. How much? Approximately 0.5%, that's it. So from equator to pole, so the g value increases. From pole to equator, so the g value decreases. Again from here equator to pole, this is another pole, right? So the g value increases. Again from pole to equator, so the g value decreases, So like this. Clear? Understood guys? Everyone? Chal. So that's what I wrote here. The value of G is minimum at the equator and is maximum at the poles. Okay, note that point. So the G is not uniform everywhere on the earth. So the G value is minimum at the equator. So and it is maximum at the pole. So if a person stands at the pole, his weight will be more than the person who is standing at the equator. Okay, so the logical question can be framed here. Understand? So chalo. So weight of a body increases as we move from equator to pole. So that's what we discussed. As G value increases, obviously weight is nothing but mg, right? Mass is going to be constant. Weight is equals to mg. So where? So the mass is a constant thing. It will not vary. So it depends on G. So from equator to pole, as the G value increases, so the weight also increases. Let's suppose at the equator, some person is standing. So some person, Chintu, is standing here. And then at the pole, some other person, Bunty. So they both have the same mass. Let's suppose he is 50 kg mass, he is 50 kg mass. So they both have the same mass. And whose weight will be more? They both have the same mass. Whose weight will be more? If they ask the question, obviously the Bunty's weight will be greater than the Chintu's weight. Why? Because the Bunty is standing at the pole, so the G value is more there, and Chintu is standing at the equator, so G value is less here. Understood? Clear? Chal. So and then the difference is approximately 0.5%. So this is the variation of acceleration due to gravity due to the shape of the earth. So no calculations, just the logic, theory based. Done? Clear guys? Chal. So let's move further. So now how the variation in G takes place due to the axial rotation of the earth. See, we know that the earth rotates about itself. So the earth rotates like this with an angular velocity omega. So generally this angular velocity omega is considered small. The earth will not rotate. No. Why? If the earth rotates like this, so then you will be thrown, you cannot stand at one place, right? So you will be thrown away from one place to another place. So that's a sure thing. So the earth rotates very slowly. So the omega is considered as very small. So now let me find the acceleration due to gravity due to the axial rotation of earth at some latitude. At some latitude. Let's suppose I have to find here. Okay, so at this latitude, let this angle be phi. Let this angle be phi. So see here, every particle of the earth, see, just imagine here, a person is standing here. So as the earth rotates, so then here the particle which is here, it rotates in which axis? It rotates in this axis, yes or no? So it rotates in this axis. If the particle is here, it rotates about this axis. So if the particle is here, it rotates about this axis like this. Okay, so clear? The earth is not rotating like this. Earth is rotating like this about its axis, right? So then here the particle which is here, or the person who is standing here, so he rotates like this. Yes or no? Understanding? Chal. So if this angle is phi, so then see the particle which is placed here, it will have two forces. What are the forces? Tell me. So towards the center of the earth, towards the center of the earth, so I can write mg is own weight. So towards the center of the earth, so his own weight will act. Yes, and then so away from this, as the person is rotating in this direction, so away the mr omega square, the centrifugal force mr omega square will act. So now if you observe the net force, see the mg is acting this side, and then so the mr omega square is acting this side. Mr omega square is acting this side. So here the net force will be this side. As omega is very small, I considered the omega is very small. Okay, so the mg value will be more and this value will be less. So obviously the net force will be towards some more value. Yes or no? So the net force will be towards some more value. So here the more value that comes here, it is the m, the g effective, mass is constant, we have to take the g effective of these two things. Yes or no? So understood, clear guys, this part? So now, so what is this g effective? So this g effective is equals to, so g minus r omega square cos square phi. So this g effective value is given by g minus r omega square minus g minus r omega square cos square phi. Clear? Understood? Chalo. So from here, one more point that you should understand. So just note it down. Okay. So one more point that you should understand. So the person who is standing here, his weight should be towards the center. This is the center of the earth, right? So his net weight should be towards the center of the earth. But here if you observe, there are two forces acting. So one is mr omega square and mg. So but the net force is like this. So that means if you are standing on the earth, so your weight is not exactly downward. It will be somewhat like this. Understanding? Clear? So you can understand from this statement, from this actual equation. So clear? Understood guys this part? So you can write that point also. So the weight will not act vertically downward, or the g effective is not vertically downward. So the g effective is not vertically downward. Clear this part? Done? Yes. So chalo. So note this one. So understood how, see the g effective actually it is decreasing, right? So g minus something you are subtracting, so that the g effective will be less than the g. So we'll see it in two different cases so that you'll understand better. So you can actually remember easily. So see here. So we have got the g effective is equals to g minus r omega square cos square phi. Yes. So now let me write for the equator, at equator and then second at pole, at poles. See, at equator means, so this value, like at equator means you take the object here, right? So this phi will become 0. So at equator means, so the phi will become 0. So if the phi becomes 0, so what will be the g effective? So the g effective will be equals to, so g minus r omega square cos square 0. So cos 0 value is 1. So this whole thing comes out to be 1. So g minus r omega square into 1. So that this value will be g minus r omega square. So this is a g effective. G effective is g minus r omega square. Okay, chal. So next, so here at poles, so the phi is equals to 90 degrees. Yes or no? So when the particle is here, so or the object is here, so this phi will become 90 degrees. So if phi is 90, so the g effective will be equals to, so g minus r omega square cos square 90 degrees. So the cos 90 is 0. So this whole thing will be 0. So the g effective will be equals to simply g. So which is 9.8 meter per second square. Okay. So this value is equals to 9.78 meter per second square, because you are subtracting this value. So which one? So g minus r omega square you are subtracting. So this r is 6400 kilometers radius of the earth, and this omega will be very small. Okay, clear guys? Understood this part? Chalo. So this is how the acceleration due to gravity changes due to the acceleration, due to the axial rotation of the earth. Okay, done. Chalo. So you can write all four cases at one place. So how the acceleration due to gravity is changing due to all four cases. So the first one, at a height h above, at a height h above the, at a height h above earth surface, so how the g value changes? So the g value is g by 1 plus h by r whole square. Yes, so r, if h is far less than the r, so then we can write, so the g dash is equals to g into 1 minus 2h by r, g into 1 minus 2h by r. So this is at a height h above, so it decreases, so the g value decreases. And then, so the second one, at a depth h below earth surface, h below earth surface. Okay, so which is, so the g dash is equals to, so g into, so 1 minus h by r, g dash is equals to g into 1 minus h by r. So here also it decreases, so here also it decreases, so the g value decreases in this case as well, right? Sure. So and then, so due to the shape of the earth, so the third one, due to shape of the earth, so where the equator, the radius at the equator is greater than the radius at the pole, so that the g at the equator will be less than the g at the poles. So where the g at the equator is considered approximately 9.78 meter per second square, and then so g at the poles is 9.8 meter per second square. So this is the one. And then due to the axial rotation of earth, due to axial rotation of earth, due to the axial rotation of earth, so we can write, so this g value is equals to g minus r omega square into cos square phi. So the g value again decreases due to axial rotation. Clear? Understood, guys? Chal. So this is all about the variation of acceleration due to gravity. So now let's move further. So the same points I wrote. So the g effective is not towards the center of the earth, it's not vertically downward at a place, so it will be somewhat tilted. So the rotation of the earth decreases the value of g, obviously. So because the g dash is equals to g minus cos square phi. So where at phi latitude we are finding. So at equator phi is 0 and g dash is equals to g minus r omega square, and at poles phi is equals to 90, so then g dash will be equals to g. So on changing the rotational speed of the earth, so the g changes everywhere except the poles. Why? Because see, so as the earth is rotating, the poles are not rotating, right? So the point which is here, so it will be constant, it is rotating about its axis, about its pole, right? So the point which is there at a pole, it is not rotating. So if it is not rotating, omega is 0. So if it is not rotating, omega is 0. So the g effective will be g only. The g effective will be g only, so that its value will not change. So on changing rotational speed of earth, g changes everywhere except at the pole. So the g value will be g at the poles. Okay, clear? Because omega is 0. So because omega is 0 at that place. Done? Clear? Sure. So let's go for the next question. So if earth stops moving around its polar axis, so then what will be the effect of the g value for body placed at south pole? So if a body is placed at the south pole, so it's already omega is 0 at the poles. So if omega is 0, so the g effective will be g only. So it will remain same. So what is the effect on the g value? So it will not change. So it remains same. The G value remains same at the pole. Clear? Understood, guys? Chalo. So the reading of spring balance corresponds to 100 newtons while situated at the North Pole, and a body is kept on it. So the record on the same scale if it is shifted to the equator. See, pole to equator, the G value decreases, G decreases, so that obviously the weight should decrease. The first thing is, so at the pole it is 100 newtons. So here it should be less than 100 newtons. So that's for sure. So can we cancel out any options? So option 2 you can rule it out. So option 4 also you can rule it out. So this change in G value is very, very small. The change in G is going to be very, very small. If the G value changes by very small amount, so the weight changes also by the small amount, because the mass is going to be constant, right? The mass is going to be constant. The weight depends on the G value. So the D decreases, so very less, right? So this decrease in G is going to be very, very less. So that's why, so 99.66 and 97.66, from 100 newtons to 97.66 means this is more. So this much will not possible. Okay. So it decreases by very small amount. So 99.66 is possible. Clear, guys? Understood? Chalo. Then, so let's move further. So let's take this question. So what's the question says here? Suppose the earth increases its speed of rotation. So let's suppose the earth increases its speed of rotation. At what new time period will the weight of the body on the equator become 0? So at what new time period? So we have to find the time period. So the time period is equals to how much? So will the weight of the body on the equator becomes 0? So weight of the body on the equator becomes 0. So what is the weight of the body on the equator first? What is the weight of the body on the equator? See, so the time period if you have to find, simply shall I write 2 pi by omega? Shall I write 2 pi by omega? So this omega you have to find. What is the omega value? So how do you find the omega value from here? See here, at new time period, so will the weight of a body on the equator become 0? Weight 0 means weight 0. So which means, shall I say that the G effective 0? Why? Because weight is nothing but mg. So where mass is a constant term, it only depends on the G. Mass cannot be 0. For any particle, mass cannot be 0. There will be some mass, right? So the only option is G should be 0. So at the equator means we should take the G effective at the equator. So what is the G effective at the equator? So the G effective at the equator is G minus R omega square. G minus R omega square, because at the equator, so the phi value is 0. So at the equator, the phi value is 0. So that cos square phi, so cos square 0, which is 1 square into 1 means R omega square into 1 is R omega square only. So this value is 0 now. This G effective is 0. So G minus R omega square from here. So R omega square is equals to G from here. So the omega square is equals to G by R, and then the omega is equals to root over G by R. Omega is equals to root over G by R. So but we need the time period. So how do we find the time period now? So the T is equals to time period. T is equals to 2 pi by omega, which is nothing but T is equals to 2 pi by omega. So what is omega? Root over G by R. Root over G by R. So we can write this as, so time period T is equals to 2 pi into root over R by G. Root over R by G. Yes. So now if you substitute the values, so T, pi and R is the radius of the earth, 6400 kilometers, and then so this one 10 meter per second square. So if you substitute all the values, So we get this T as 84 minutes. This T, this is a standard result, you should remember, guys. So T is equals to 84 minutes. So which is nothing but so 24, 60 plus 24 means 1.4 hours approximately. Approximately 1.4 hours. Clear? Option 4 is the correct one. Done. So this is a standard result, you can remember directly. Okay. Chalo. So understand the procedure first. Done. Chalo. So let's move further. So let's go for the gravitational potential. Till now we have seen the gravitational force. What's the gravitational force between the two masses? So any two masses in the universe, they attract each other by the force of gravitation. So which is equals to Gm1 m2 by r square. So that gravitational force follows the inverse square law, where so the force of gravitation is inversely proportional to the r square, right? So done. And then later we have also seen what is the gravitational field, right? So the gravitational field, so it is Gm by r square we discussed, right? So now we are going to discuss so the gravitational potential. So what is the gravitational potential or the potential difference? So let's suppose there are 2 points x and y. So now if you have to bring a mass m from so point y to point x, so this is a small mass m, so this mass should be brought to this point without changing its kinetic energy. So that means it has to be brought so very slowly, very slowly. So then only so its change in kinetic energy is 0. Then only its change in kinetic energy is 0. So this has to be brought in such a way that so the change in kinetic energy should be 0. Okay. So then the gravitational potential, we define it with V. Okay. So V final minus V initial. So final minus initial. So now from where you are bringing the mass? So from where you are bringing the mass? So from y point to the x point. Yes or no? So the understanding. So here let me write, sorry. Fine. So G into, so from where we are to, from where to where you are bringing the mass? So y to x. So that means so the let me write this way. So you are bringing it from y to x. So that's why so the final is x and initial is y. So generally we write the formula as so V is equals to Gm by r minus Gm by r. So from here, so from where to where you are bringing? So the small distance. So the mass upon the distance. Okay, mass upon the distance. Okay. So from where to where? Sorry, my bad. So from where to where you are bringing? See, let me compare this way. You can understand easily. Chalo. So in grade 10th level, you studied. Let's suppose there are 2 points x and y. So at y, so there is a charge q. So then you are bringing the charge from y point to the x point, right? So then the electric potential you studied, right? What is the electric potential? So which is nothing but so the Vx final minus Vy. So how much work you are doing? How much work you are doing from where to where? Y to x. So y to x by, so in bringing the charge q, so w by q. So here also the same thing. So how much work you are doing in bringing this mass from y to x by, so the mass m. So how much work we are doing in bringing this this mass from y to x. So this is actually the potential difference. This is actually the potential difference in terms of mass. This is in terms of electric. Okay, clear guys? Done? Chal. So work done in bringing the mass. So this is a potential difference. So generally we write so the potential difference, not potential difference, the potential, gravitational potential. So whose formula V is equals to minus Gm by R. So minus Gm by R. So minus Gm by R. Clear? So note this point first. So this is a direct formula, you should remember, guys. So what are the units you can write? What are the units that you can write? Or else we'll write this formula in the next slide due to the point mass. So okay, fine. So you can. So units. So work done, joule per mass kg. So now if you need the gravitational potential at a point, see. So if we need the gravitational potential at a point, so then what we assume is, so we bring the mass from infinity distance, some infinity distance. So this is the infinity. So let's suppose here we consider some mass m. So now you have to bring this to point A. So very slowly, in such a way that the change in kinetic energy should be 0. So then we can write here, so the potential difference, which is VA minus final is VA, initial is from infinity you are bringing. So which is equals to, so the work is done from where to where? Infinity to, so the point A, by in bringing the charge m. So generally in physics, so the potential at infinity is considered as 0. The potential at infinity is considered as 0. So this will become 0. So that, so the VA minus VA is equals to the work done from infinity to A by the mass m. This is the potential at a point. So potential difference is when, if two points are at a certain distance. Let's suppose if I take from X is one, A is one point and B is one point. So there is mass at B. So you are bringing to A, where these A and B are at some finite distance. Then you can write the potential difference. So what is the potential difference? Final minus initial. Finally you are bringing it to A from where? B. So which is equal. So the work is done from where to where? B to A. So this work should be done very slowly. Sorry, in bringing the mass. Fine, clear? Chalo, done. This is about the potential difference and the gravitational potential at the given point. So now, what is the gravitational potential due to a point mass? So this is a point mass m. So at a distance r, at this point P, we have to calculate the gravitational potential. So the gravitational potential formula is given as minus Gm by R. Minus Gm by R. So this is a gravitational potential due to a point mass. So what is this one? The gravitational, remember this formulas. Gravitational potential due to point mass. Gravitational potential due to the point mass. Done. And one more thing, so we already studied the electric field. So what is the electric field due to the point mass? E is equals to Gm by R square, remembered? So this electric field is a vector quantity. The electric field is not electric field, gravitational field, sorry. So this gravitational field is a vector quantity, Gm by R square. So this electric potential, it is a gravitational potential due to the point mass, it is a scalar quantity. It's a scalar quantity. Okay. So if you have to find the gravitational potential due to the system of masses, so simply you can do the scalar addition. Okay. So this one is a vector quantity. The gravitational field is a vector quantity and gravitational potential is a scalar quantity. So gravitational field due to a point mass is Gm by R square, where the gravitational potential due to a point mass is minus Gm by R. Okay. R is the distance where you are finding the gravitational field from the point mass. Okay, chalo, so done. So now if we have to find the gravitational potential due to system of point masses, so at this point P, if we had to find the gravitational potential due to the mass m1 which is at a distance r1, due to mass m2 which is at a distance r2, due to mass m3 which is at a distance r3, and like that till so by the mass mn, so which is at a distance rn. So simply you can go for the scalar addition. Simply you can go for the scalar addition because the gravitational potential is the scalar quantity. Okay, so the net gravitational potential at point P is equals to, so the gravitational potential due to mass m1, the gravitational potential due to mass m2, so the gravitational potential due to mass m3, so till the gravitational potential due to mass mn. So what we can write this one, first one, minus g m1 by, it is at a distance r1, so plus into minus minus, minus g m2, it is at a distance r2, and then plus, so into minus minus, so minus g m3 by r3, so till, so minus g mn by the distance rn. So you can take minus out here, so we can write gm by r1 plus gm by gm1 by r1 plus gm2 by r2 plus gm3 by r3, so till gmn by rn, till gmn by rn. So this is the gravitational potential at, so the point P, at some point P. Clear? Understood guys, everyone? Chalo. So let's go further. So let's go for the question number 4. What's the question says here? So find the gravitational potential at the center of the triangle. So find the gravitational potential at the center of the triangle here. So I can say that, so let's suppose from here to here the distance, let it be r, from here to here r, from here to here it's going to be r s. So now how do you find this r distance? So simply first let this be point O. So the gravitational potential at the point O will be, it is due to the gravitational potential due to, so the point mass m, so and then due to the, so due to all these three, so I can write like, so minus gm by r, so the second one also minus gm by, so r, and then the third one also minus gm by r, from center to here r distance, so which is the potential, net potential at O is minus 3 gm by r. So now the thing is, what is this r? So how do you find this r value? So use some maths here. So if you can take this one, so then we can write this as 30 degrees. So this distance will be a by 2 from here to here. So write this triangle aside. So we can write like, so this is the 30 degrees. So this is a by 2. So this is r. So adjacent I know, hypotenuse I know. So let me use the cos 30 degrees. So cos 30 degrees is equals to r by a by 2. Sorry, adjacent by hypotenuse, right? So adjacent is a by 2 by r. So from here cos 30 value, so which is root 3 by 2. So which is equals to, so this is a by 2r, a by 2r. From here we need 2 to cancel. So we need r is equals to a by root 3. So we have got r value as a by root 3. So now substitute that r value here. So minus gm into r, minus 3gm by a root 3. So which is nothing but minus 3 root 3 gm by a. So this is minus 3 root 3 gm by a. So 3 root 3 gm by a is there in the option 3. Clear? So simply take the magnitude. So minus 3 root 3 is there only in the one option. So that is option 3, guys. Clear? So ignore this a. So this is chalo, done. Clear? Chalo. So let's move further. So try this question. So what's the question says? Infinite number of bodies, each of mass 2 kg, are situated on x-axis at a distance 1 meter, 2 meter, 4 meter, 8 meter respectively from the origin. So the resulting gravitational potential due to the system at the origin will be, yes, see here. So this question, so consider this is a x-axis. Consider this is a x-axis where, so this is the origin. So now from origin at 1 meter, so there is 2 kg object is placed at 1 meter, and then at 2 meters again from origin. So here it is one more, from here to here it is 2 meters, okay, and then so then 8 meters, so 3, so from here let's suppose some here, so again 2 kg mass is placed. So then next at 16 meters, so some 2 kg mass is placed. So like that, next at 32, so like that. So here, what is the net gravitational field at this point O? The net gravitational field at this point O. So what we can write? So the net gravitational field at O is, so the first one is G into, so the mass, let it be small m, so it is at a distance 1, right? The second one, G mass m, it is at a distance 2, right? So and then the third one, minus gm, which is at a distance 4. So and the fourth one, gm, it is at a distance 8, right? So then minus gm, so which is at a distance 16. So it goes on, so up to infinity. See, if you observe, so this is going to be, this sequence is in the form of the shall I say, so the geometric progression. This series is in geometric progression GP. This series is in geometric progression GP. So let me write this again here. So the net gravitational potential at O is minus gm by 1, minus gm by 2, minus gm by 4, minus gm by 8. So and then goes on. So here, if it is a geometric progression, it is in GP. So now in GP, so the first term A, we can write it as, the first term A is equals to minus gm by 1, and then so what is the common ratio R? So what is the common ratio R? Which is equals to, so second term by first term, right? So A2 by A1, which is gm by 2 minus gm by 2, so minus gm by 1. So here this gets cancelled, gm gets cancelled, so which becomes, so 1 by 2, so this will be 1 by 2 is left. This is the common ratio, 1 by 2. So now what is the summation of infinity terms in the case of geometric progression? So the summation of infinity terms in the case of geometric progression is, so S infinity is equals to A by 1 minus R. A by 1 minus R. So what is A? So the first term, so which is minus gm by 1 by, so 1 minus R, which is 1 minus 1 by 2. So 1 minus 1 by 2, right? So here the S infinity is equals to minus gm by 1 whole by, so it is 1 minus 1 by 2 is 1 by 2. So from here, so the S at infinity is equals to, so this 2 will go up, it will be minus 2 gm. So here the mass value they gave right in the question, 2 kg. So substitute, so the summation of infinity terms will be equals to minus 2g. In place of this mass, substitute 2 kg again, so that we get this total is minus 4g. So the summation is nothing but the net gravitational potential at O is minus 4g. So this is a net gravitational potential at point O, origin. Option 4 is the correct one, guys. Clear? The concept is easy, but you have to do these mathematical calculations. You should get this idea in the examination. Clear? Chalo. So let's move further. So now what is the gravitational potential on the axis of the uniform circular ring? So see here. So this uniform circular ring, for this what we do is simply we cut, so here the small mass dm. So due to this, let's suppose this is at a distance some small r. Let's suppose this is at a distance some small r. So this uniform circular ring has radius r. Okay. So from here I can write like, so this r is equals to square root of r square plus x square, because this is a right angle triangle. Yes or no? This is a right angle triangle. R is equals to square root of r square plus x square. We can write that. So what is the gravitational potential? Gravitational potential due to, so small mass dm, small element, let's say small element dm b dv. So the small gravitational potential is dv. So what is the dv now? So the dv is equals to, so minus g dm by, so minus g dm by r. Yes or no? So this is due to only small element dm. So if you need total gravitational potential, so which is, so the integration of dv is equals to, so the integration of g dm, let's take minus out, minus g dm by r, minus g dm by r. So g is a constant and the gm, so what is the total mass gm we can write? So the total mass is going to be, let this half some mass m and radius r. So the g dm 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 if you add, so the total mass of the ring, so we can write from here, so the integration of dv is v, that net potential is equals to minus gm by, so r, so the distance r, right? So from here, so what we can write? So minus gm, so what is r here? So square root of r square plus x square. Done. Understood guys? Clear? Chalo. So note that point. Everyone fast. Done. So this is on the axis of the ring we call. So therefore, so the gravitational potential on the axis of a uniform circular ring, which is minus gm by, so square root of r square plus x square. On the axis of a uniform circular ring of mass m and radius r is square root of minus gm by square root of r square plus x square. So x is a where you are finding the gravitational potential. Okay. So did you guys remember the gravitational field formula? Did you guys remember the gravitational field formula? The E is equals to gmx by x square plus r square whole to the power 3 by 2. This is the gravitational field due to the uniform circular ring. So and this is the gravitational potential due to the uniform circular ring of mass m and radius r. Done now? Clear? Chalo. Hope it is clear for everyone. Just remember the formulas. So now let's go for the gravitational potential due to the hollow sphere or spherical shell. So here this is a hollow sphere or spherical shell which is of mass m and radius r. So if we, in three cases we can find the gravitational potential. So the first one is outside. The first one is outside where r greater than r. So the gravitational potential outside the spherical shell is simply minus gm. So let this mass be m. So minus gm by r. So it's a minus gm by r. And then the second, at the surface, on the surface of the spherical shell, so it's going to be r is equals to r. So here the potential at the surface will be equals to, so minus gm by r, minus gm by r. So this is the second one. And in the third case, so then the third case, so inside, So which is equals to, so the gravitational field inside the spherical shell is going to be 0. Okay, chalo. Done. Inside r less than, sorry, spherical shell, right? Sorry, my bad. R less than r, so it's going to be same as of the surface. So minus gm by r. So inside and inside to the surface, so the potential remains same. So from inside to the surface, so the potential remains same from here to here, everywhere. The potential, the gravitational potential remains same. So this is also called the equipotential surface. This whole thing is a equipotential, means the potential is same inside the spherical shell, so which is of mass m and radius r. So outside it is inversely proportional to r, on the surface it is capital R, and inside also it is capital R only. So from here to here it is constant, and then from here it becomes decreases. Done. Chal. So if you draw the graph, so see here, so if you draw the graph, so inside it is maximum and constant from inside to this point. So and then outside it decreases like this. So outside it decreases like this. Clear? So sometimes the graph can also be given below the x-axis. So the graph can be given below the x-axis. Why? The value is negative, right? So that's why they can also give like this. This is x-axis and this is y-axis. So here they might give like this. So this is also correct, because the gravitational potential is negative. Okay na? So either this graph or this graph. So both are correct. Okay na? Done? Chalo. So now let's go for some shell concept. Let's understand this concept, guys. See, this is a shell. So I'm taking the, yeah, see here. So this is the center point O. So this is of mass m and this is of mass m, and I am taking, so this has the radius 2r, and then this has the radius r. This has a radius r. So now due to this shell, if I have to find the gravitational potential at some point y here, and at some point x here, and at some point O. So my question is, I'll write the question. Find net gravitational potential. Find net gravitational potential. Net gravitational potential. So at point x, point y, and O. O means at the center. Okay. So I am taking here, let's say, so this y point is at a distance 3r total, and then let's take this x point somewhere around here. So the x, to avoid the confusion, I am taking x point somewhere around here. So this x point is at a distance, let's say 1.5 r. So the values I am giving randomly. So because this is r, obviously this should be greater than r, so that I am taking 1.5 r here. This is a radius, small radius r. So first let's find at the outside point v. Let's find the net potential at point y. So the net potential at point y. So here the potential will be there due to the first shell and the second shell. Yes or no? So the, let it be the first one A, let it be the B. Yes or no? So let it be the A, let it be B. So the potential due to A will be there, and potential due to B also will be there. For A, for shell A, it is outside, and for shell B also it is outside. For shell B is also it is outside. For shell A it is outside, and for shell B is also it's outside. So for outside, what's the formula we know? So minus G, mass is m by, so r. So here also minus G m by r. Yes. So now what is this distance? Small r. From the center of each shell, from A shell center to this point, the distance is 3r. Yes. Minus from B shell center, their both center is same, so it's a concentric shell. So concentric shell means they will have the same common center, right? So from here to here also the distance is going to be 3r. So 3r and 3r, so which is minus 2gm by 3r. So this is a potential at y point. Clear? So done. So just values you can ignore, just you understand the concept, guys. So now next, so let's find the gravitational potential at point x. This is a point x. So now x point I am finding. So the gravitational potential x will be equals to, so the gravitational potential due to the A shell, and then gravitational potential due to the B shell. Yes. For A shell, this x point is outside. For A shell, this x point is outside. Yes or no? For B shell, this x point is inside. Yes. Done. Now you can write the answer. So outside formula minus gm by r. Minus gm by r. And then inside minus gm by radius of that shell. What is the radius of this B shell? So B shell has a radius 2r. So yes or no? From inside to, for the B shell, from inside to till here, the gravitational potential remains same. From here, everywhere it remains same. How much? Minus gm by 2r for the outer shell. Yes. So the same thing, minus gm by, what is this small r? Small r distance is from here to here, because for the shell A it is outside. So the small r is this distance, which is 1.5 r. So which I am writing it as 3 by 2 r. 1.5 r means I am writing it as 3 by 2 r minus gm by 2 r, right? So then, so this is minus 2 gm by 3 r. So minus gm by 2 r. So from here, so the LCM is 6 r. So it's going to be 2 times. So 2 means minus 4 gm, and then this is 3 times. So minus 3 gm. So which is minus 7 gm by 6r. Minus 7 gm by 6r. Done? Clear? Understood, guys, this part? Shall. So now let's find at A. Let O. Let's find at the point O now. So the gravitational potential at O will be equals to, so the gravitational potential due to shell A and gravitational potential due to shell B. So for the shell A it is inside, and for shell B also it is inside. So for the shell A it is inside, and for shell B is also it is inside. That's it. So now for the shell A we consider the radius as small r, and for shell B, which is 2r. That's it. So now the LCM is 2r. Here it is minus 2 gm minus gm. So which is minus 3 gm by 2r. Minus 3 gm by 2r is a potential at O. Done? Clear, guys? So this is a potential shell concept you should understand. Done, everyone? Chalo. So let's move further. So take this question. What's the question says? A particle of mass m is situated at the center of the spherical shell of same mass and radius a. So there is a spherical shell. This is the spherical shell whose mass is m and whose radius is a. Now, so and then one more mass, capital M, this particle which is of mass, same mass m, is situated at the center of the spherical shell. So now we have to find the gravitational potential situated at a by 2 distance from the center. So a by 2 distance from the center means somewhere around here you have to find. Okay. So let this point I am calling it as some x point I am calling it. Okay. So what is the potential at x? It will be due to, so the potential due to point mass, the potential due to point mass plus, so the potential due to the shell, the potential due to the point mass and potential due to the shell. So for the point mass, it is outside. For the point mass, it is at a distance a by 2. And then for the shell, so the potential, it is inside. See, or else you need not to write inside or outside. So don't, because from the, what is the gravitational potential due to the point mass formula? Minus gm by r. We have seen, right? Where is that? So the gravitational field due to the point mass minus gm by r, right? So then simply I can write here that. So what's that? The gravitational potential due to the point mass is minus g due to which mass? Capital M mass. So which is at a distance how much? A by 2, right? So plus, so minus I am writing because due to the shell inside. So inside it's going to be, simply we can write its radius. The radius is a, right? Done. That's it. So we can write, so 2 will go up, minus 2 gm by a minus gm by a. So which is minus 3 gm by a. Yes, minus 3 gm by a. Option 1 is the correct one, guys. Done. Chal. Simple questions. Let's move further. So let's take one more question. So what's the question says? Two concentric shells have mass m and m, and their radii are capital R and small r respectively. So first let's draw the diagram. So here, this is one shell and this is one more shell. So whose masses are? So let the outer one is capital M mass, so and the inner one is small m mass. And then the radii of the outer one, let's take this as capital R, and the radius of the inner one as small r. So now, what is the gravitational potential at the common center? So at this point O, see here, simple question. The gravitational potential at center O, it will be due to, so it will be due to, let it be the shell A, let it be the shell B. So due to shell A plus due to shell B. For the shell A, it is inside. For the shell B also, it is inside. Yes or no? So minus gm, so the minus g, for shell A has the mass small m. Yes or no? Shell A has the mass small m. So what is the radius of the shell A? Small r, minus. So for the shell B has the mass capital M by. So what is the radius of the outer shell? So which is capital R. So from here minus g I can take it out. So minus g, if I take it out, so that m by r plus m by r. M by r plus m by r. So minus g m by r minus g m by r minus g m by r minus m by r. No, minus g here, not f. From where this f has come? This is g. So minus g m by r plus small m by r. Yes. So option 4 is the correct one, guys. Done. Clear concept? Chalo. So let's move further. So now let's go for the gravitational potential due to the solid sphere. So solid sphere where, so the mass will be spread throughout its volume. The mass will be spread throughout its volume. It has mass m and let's say radius r. It will have some density rho. Okay. So now again there's three cases. So the first one outside. The first one, let's say outside, where r is greater than the r. So which is the potential outside is equals to same formula minus gm by r. It is inversely proportional to the distance r. And then, so at the surface where r is equals to r, so the potential at the surface, so is equals to surface is equals to minus gm by capital R. Okay, chalo. So the inside one, you should remember the formula, guys. So for the inside one, the potential inside, which is minus gm by r cube into 3 by 2 r square minus 1 by 2 r square. So 3 by 2 r square minus 1 by 2 r square. So everyone should remember this formula. Everyone should remember this formula. Minus gm by r cube into 3 by 2 r square minus 1 by 2 r square. So here one more thing. So what is the relation between the potential at the center and potential on the surface? So the potential at the center. At center, shall I say at center, so the small r will be equals to 0. At center, the small r will be equals to 0. So the potential at center, we can write, substitute the small r 0. So this whole term will become 0. Minus gm by r cube into, so here 3 by 2 r square will be left. So here r square and r cube gets cancelled. So 1 r will be left. So v at the center will be equals to, so minus 3 by 2 into gm by r. So which is nothing but, so the potential at the center of the solid sphere will be equals to, so minus 3 by 2 times potential at surface. This one I can write it as the potential at the surface of the solid sphere, which is minus gm by r, right? So here you can simply write, you can take out the minus also because we are writing the surface potential. So here 3 by 2 times the potential at the surface, because at the surface means here the formula already includes minus gm by r. Done? So this is a relation. So for the solid sphere, inside its gravitational potential will be there, but for the hollow sphere, inside it's going to be same as on the surface. That's the only difference. Okay, outside it is minus gm by r for both the cases, and on the surface it's same for the both the cases, minus gm by r, minus gm by r. But for a hollow sphere, the v inside is same as of the surface, but for solid sphere, so the v inside is this one, the formula. Done? Clear? Chalo. Good. So can we, let's draw the graph, guys. So let's draw the graph for this. See here. So first thing is the v inside, or else let's write like this. First, this relation you can remember. So v at the center is equals to 3 by 2 times v at the surface, right? V at the surface. So that means at center it will be maximum, and then this is at the surface, and then from outside it decreases like this. Let's write this way. So from center to surface, so this is a formula. Center, this is 3 by 2 times the surface. So this is the potential at the surface, and then from here, from surface it decreases like this. From surface it decreases, the potential is inversely proportional to the r. Okay now? Clear, guys? So v at the surface is what? Simply 3 by 2 times, minus gm by r. Okay, so v outside, write the formulas along with me. So minus gm by r. So where this small r is the distance from where you are finding the gravitational field from the center of the sphere. Okay, and then so v inside also you can write the formula. So which is minus gm by r cube into, so 3 by 2 r square minus 1 by 2 small r square. That's it. Clear? Done this part? Sure. So let's move further. So the variation of gravitational potential of earth, earth means it's a solid sphere. It's a solid sphere. So with the distance from the center of the earth. So from the center of the earth, see here. So here they gave it in negative axis. So as I discussed previously, so they can also give it in the down. So it's constant here, no. So it's decreasing, no. See here. So at the center it will be maximum. So then it decreases to the surface. From surface it again decreases. Option 3 is the correct one. Clear? Understood, guys, everyone? Chal. Now, what is the relation between the gravitational field E and the gravitational potential V? So what's the relation between, so the gravitational field E and gravitational potential V? So E is equals to minus dV by dr. Remember this. So E is equals to minus dV by dr. So if you want to find the gravitational field in the x direction, so simply you can write minus dou Vx by dou x. So the gravitational field in the y direction, it is minus dou Vy by dou y, and then dou is nothing but the partial differentiation. Okay, so the gravitational field in the z direction, if you require, so dou Vz by dou z. So what is dou? It's a partial differentiation. That's it. So dou is partial differentiation. Same differentiation formula only you can use. So we'll solve the question so that you'll understand better. This is a partial differentiation. Done? Clear, guys? Chalo. So let's move further. So V is equals to 2 by x cube and find the gravitational field at x is equals to 6. So what they are saying, they gave the gravitational potential and they are asking gravitational field. So what's the formula we know? The gravitational field can be written as dou V dV by dr. Here the gravitational potential is only given in the x direction. Yes or no? So the gravitational potential is only in x terms they gave. So let's suppose at x is equals to 6 I required. So the gravitational field in the x direction is equals to, so minus dou Vx by, sorry. So let's write this one. So minus dou Vx by dou r, dou x, minus dou Vx by dou x. So which is nothing but minus dou by dou x of, so what is the potential in the x direction that is given? 2 by x cube, right? So 2 take it out, so minus 2 into, so I can write it as dou by dou x of x to the power minus 3, x to the power minus 3. So minus 2 into, so here minus 3 into, so x to the power minus 3 minus 1, x to the power minus 3 minus 1. So that I can write this as, so minus 2 into minus 3, which is 6 into, so x to the power minus 4, which is nothing but 6 by x to the power 4. So 6 by, so what is at x is equals to 6 we required, right? So 6 means 6 into 6 into 6 into 6. So which is 1 6 1 6 gets cancelled, 1 by 36 into 6, which is 216, right? So the gravitational field at x is equals to 6, this one. So which is equals to, so 1 by 216. So we got positive only. So put the option 4. See, don't get confused between the option 3 and 4 again. Okay, we already did this with the negative symbol formula only. Done. Chalo. So this is also done. Next. So let's try this question. V is equals to x square minus y square. So now find the gravitational field at 1 comma 1. So how do we find? First, let's find, so in the x direction, let's find in the y direction. So then we can write, so the net gravitational field is equals to actually Ex I cap plus Ey j cap. In this format we should write. Okay. So first let's find Ex. So what's the gravitational field in the x direction? So which is equals to, so minus dou Vx by dou x. Simple formulas. So minus dou by dou x of, what is Vx? So let's write the total V value, x square minus y square. So the differentiation of y square with respect to x is 0. So the second term is 0, however, minus, so the differentiation of x square is 2x. The differentiation of x square is 2x. So the other one is 0. So no need to write. So this is the gravitational field at x. So next, so or else you can substitute at x is equals to, at x is equals to how much we required? 1. So the x component is 1, right? So here minus 2 into 1, which is minus 2, let's write. Next, so the gravitational field in y, Ey, is equals to, so minus dou v by dou y, which is minus dou by dou y of, So what is Vy? So write the total V value, x square minus y square. So however, the differentiation of x square with respect to y is going to be 0 minus. So the y square differentiation is minus is already there here, minus is already there. So then 2y, yes, so minus of minus plus 2y. So this becomes, so this is the gravitational field at y. So now we need at y is equals to 1, right? At y is equals to 1. So 2 into, in place of y you substitute 1, which is 2. So that the total gravitational field will be equals to Ex I cap plus Ey j cap. So which is nothing but Ex. What is Ex? Minus 2 I cap plus Ey. So what is Ey? 2 j cap minus 2 I cap plus 2 j cap, minus 2 I cap plus 2 j cap. Option 4 is the correct one, guys. Clear, everyone? Chal. So let's move further. See, and the reverse process. See, we have discussed just now. So the gravitational field is equals to minus dv by dr. So don't put vector quantity here. This is a scalar quantity. So shall I write from here the dv is equals to minus e into dr. So the dv is equals to minus e into dr. Shall I write? So from here, let's suppose this position, this is a position vector you can write. Okay. So shall I write, if the gravitational field is given in this way, Ex I cap plus Ey j cap and then Ez k cap, if the gravitational field is given this way. So and then if the position vector also has the components, so let's suppose dx I cap and then dy j cap and then dz k cap in 3-dimensional space. So then we can write this as, so dv is equals to minus, so minus, so let's find the total gravitational field. So let's do the integration on either side, minus e dr, so which we can write it as, so the net gravitational field, so which is equals to, so Ex dx, so total negative I am taking out, so Ex dx from x1 to x2 plus integration y1 to y2, so Ey dy s plus, just I am taking these two into Ex I cap into dx I cap, so which is Ex dx, I cap in I dot I is 1. So directly I am writing, so that is minus again. So again the next one minus, the next one minus, I am taking minus out. Okay, basic math. So and then from z1 to z2, so Ez dz, that's it. So that means if we have to, if, see what's the understanding here, if the gravitational potential is given, if we have to find the gravitational field, just differentiate. And then if the gravitational field is given, if the gravitational field is given in x, y, z, so then if we have to find the gravitational potential, simply integrate the reverse process. Okay, chal. So here let's take one simple question. You can solve it easily. So what's the question says? The gravitational field is given 9 by x square I cap. That means only in the x direction is given. So now we have to find the gravitational potential at x is equals to 3. So first the gravitational potential in the x direction is minus integration of Ex dx. There is no y term, so no need to take, because if you take also that will be 0. Okay. So minus I can write. So the integration of, so from where to where? So here Ex is 9 by x square into dx, from where to where? So 0 to 3. So find initial to final at x is equals to 3 if v at infinity is 0. So initial to final. So then because you are bringing it from the infinity point to the x is equals to 3 point, then only potential will develop, right? Understanding? So 9 is constant. So and then the integration of x to the power minus 2 dx. So here from 0 to 3. So minus 9 into, so how do you write the integration of this one? So x to the power minus 2 plus 1 by minus 2 plus 1 into dx. So already we did the integration, right? So yeah, so minus this one. So which is nothing but we can write minus 9 into, so x to the power minus 1 by, so minus 1, this one, minus 2 plus 1 is minus 1. So here minus minus cancel. So 9 into, so 9 into, so we can write this is 0 to 3. So 9 into 1 by x. So from 0 to 3. So we substitute upper limit minus lower limit. So 1 by 3 minus 1 by 0. So 1 by 0 is infinity, right? So so then this is going to be, so 9 into 1 by 3. So which is the final answer 3. So we get the final answer as 3, right? So you can directly substitute this part. Done, everyone? Clear? Understood this logic? The first thing? Chalo. So can you solve the next question now on your own? Oh, sorry, the question is not there. Huh? Okay, fine. So that's it, guys, from my end. So we have completed the lecture number 3. Okay, so in the next class, so we are going to discuss with the gravitational potential energy and the escape velocity of the satellite. Okay, so till then, keep studying. All the very best. Bye. Take care.